Good morning, students. Let's begin our new lesson. In this lesson, we will learn solving IP by branch and bound method. And we remember in last lessons, we have studied how to set up an IP program. So in these lessons, we studied how to solving an IP program. In this class, we focus on two sections. Section 4, some perspective on solving integer programs. Section 5, the branch and the bound technical for BIP. Section 4, some perspectives on solving integer programs. It may seem that IP programs should be relatively easy to solve. After all, linear programs can be solved externally efficiently, and the only difference is that IP programs have far fewer solutions to be considered. In fact, pure IP programs with a bounded feasible range are guaranteed to have just a finite number of feasible solutions. Unfortunately, there are two fallacies in this line of reasoning. One is that having finite number of feasible solutions ensures that the problem is readily solvable. Finite number can be tremendously larger. The second fallacy is that removing some feasible solution from the linear program will makes it easy to solve. To the contrary, it is only because all these feasible solutions are there that the guarantee can be given that there will be a corner point feasible solution that is optimal for the overall problem. This guarantee is the key to the remarkable efficiency of the simplex method. As a result, linear programs generally are much easier to solve than IP programs. Because IP programs are in general much more difficult to solve than linear programs, sometimes it is tempting to use approximate procedure of simply applying the simplex method to the LP reduction and rounding the non-integer values to integers into the result solution. Now we see rounding solutions. This approach may be adapted for some applications, especially if the values of variables are quite large, so that rounding creates relatively little error. However, you should beware of two pitfalls involved in this approach. One pitfall is that optimal linear program solution is not necessarily feasible after it is rounded. Often it is difficult to see in which way the rounding should be done to return feasibility. It may even be necessary to change the value of some variables by one or more units after rounding. To illustrate, consider the following example. We see this example. This example is maximum j equal to x2, and this is the subject to constraints. And we note that x1, x2 are integer numbers. And in these programs, we not think about the integer number, so we think it as LP programs, and it is LP reduction. We simplexed by simplex method. We get this is the optimal solution. If we rounding, the rounding point is this or this, and we notice that this rounded solution are not feasible. It's not in this feasible range. So from this example, we note that the rounded solution generally is not a feasible solution. Now we see example 2. This example we notice that x1, x2 is all integer 2. So we solve LP reduction. LP reduction under the optimum solution is this, and the rounded solution is this, but the IP of optimum solution is this. So we noticed in this example, the rounded solution is that is feasible solution, but it's not optimum IP solution. So even if the optimum solution for the LP reduction is rounded successfully, there remains another pitfall. There is no guarantee that this rounded solution will be the optimum integer solution. So generally, the rounding solution is not the IP optimum solution. So because of two pitfalls, a better approach for dealing with IP problems that are too large to be solved exactly is to use one of the available heuristic oscillograms. These oscillograms are extremely efficient for large problems, but they are not guaranteed to find the optimal solution. However, they do tend to be considerably more effective than rounding approach just discussed in finding every good feasible solution. The most popular model for IP oscillograms is to use the branch and bond technique and relate ideas to implicitly enumerate the feasible integer solution, and we shall focus on the branch and bond technical approach. So now we introduce section 5, the branch and bond technique for BIP. Because any bounded pure IP problem has only a finite number of feasible solutions, it is natural to consider using some kind of enumeration procedure for finding an optimal solution. Unfortunately, as we discussed in the preceding section, this finite number can be and usually is very, very large. Therefore, it is imperative that any enumeration procedure be cleverly constructed so that only a tiny fraction of the feasible solution actually needed to be examined. For example, dynamical program provides one such kind of procedure for many problems having a finite number of feasible solutions. Another such approach is provided by the branch and bond technique. So we importantly introduce branch and bond technique. The basic concept underlying the branch and bond technique is dividing and conquer. Since the orange large problem is too difficult to be solved directly, it is divided into smaller and smaller sub-problems until these sub-problems can be conquered. This dividing is done by partitioning the entire of the feasible solution into smaller and smaller subsets. The conquering or forcing is done partially by bounding how good the best solution in subset can be and then discarded the subsets. It is bound indicates that it cannot possibly contain optimal solution for the origin problem. We should now describe in turn these three basic steps: branch, bounding, and fastening. And we explaining in this prototype example. We see example 1. We need to solve these models, and this model is xj is all binary variables, so it is BIP model. Step 1, branch. When you are dealing with binary variables, the most straightforward way to partition the set of feasible solutions into subsets to fix the variable one of the variable, say x1 at x1 0 for one subset and x1 equal to 1 for the other subset. That is, in these programs, we first to solve the LP problem and delete or binary variables, and we form the LP reduction, and we solve these problems, get the optimal solution. And we notice that in this optimal solution, the x1 is not binary and it is not integer. So we branch x1. Set x1 equal to 0. Set x1 equal to 1 to dividing sub-problems. So in this plan, we notice that we first solve the problem, we delete all binary restrictions, and this is the LP reduction, and we can solve by simplex method. We get the optimal solution is x equal to optimal value equal to 16, and we noticed in this optimal solution x1 is not integer, so we dividing branch by x1. We set x1 equal to 0, x1 equal to 1, so dividing into two sub-problems. And delete other variable binary restrictions. So this is LP model 2. This is LP model 2, and we get this model B1 and B2. These two subprograms is also LP program. We get the optimal solution. X B1 optimal solution is x equal to 0, 1, 0, 1, and this is binary solution, so it meets the requirements. And solve the B2 LP reduction problems, we get optimal solution. It's not a binary solution, so it is not meet the requirements. And we notice that in B1 model, it additional constant x1 to 0. In B2 problem, we additional constant x1 to 1. So this is the two sub-programs. And we notice that B1 is a binary solution, so we can stop here. We get the binary solution. But we notice that this optimal objective function is greater than z equal to 9. So we need to continue branch. And we notice that in B2 problems, the objective number is 6, and x2 is not integer 2. So we set all dividing branch by x2. We set x2 equal to 0, x2 equal to 1, and we get two sub-problems, C1 and C2, and we solve the C1 problem, C2 problem. C1 problem, we notice that we added another constant, x2 equal to 0. In C2 subprogram, we add this constant, and we get these two reduction problems, the optimal solution. This is the optimal solution, and we notice that the x3 or x4 is not binary true, and we notice the objective function. This is the great This is the great. So for these problems, we need to continue dividing branch 2. And for these problems, we continue to branch set x3 equal to 0, x3 equal to 1. And this reduction problem is no feasible solution, so we cut this branch. And this problem, this subproblem, C is also great. 16. So we continue branch 2, and we set x4 equal to 0, x4 equal to 1, equal to 1. So we note these two subproblems that this is no feasible solution. We cut this branch, and these subproblems we get the binary solution, and stop here, So we have finished this solution of the BIP problems, and from this graphic we get this is the maximum. This is the maximum, and the solution is binary. So this solution is meet the requirements of this model. So we get this is the optimum solution of this model. So we see the preceding steps. Step 2, bounding. For each of these subproblems, we now need to obtain a bound on how good its best feasible solution can be. The standard way of doing this is to quickly solve a simple reduction of the subproblems. In most cases, the reduction of the problem is obtained simply by deleting one of the constraints that had made the problem difficult to solve. Bounding. And we get a binary solution. We can bounding. Objective is 9. And if you get another binary solution, you can bounding 2. Bounding and discard this branch. Step 3, FASTMIN. A subproblem can be conquered, dismissed from further consideration in 3 ways described below. Summary of FASTMIN test. A subproblem is famous if test 1 or case 1 is bounded less than JC. JC is the current object function. Or in test 2, its LP reduction has no feasible solution. Or test 3, the optimum solution for its LP reduction is integer. So in these 3 cases, we can FASTMIN or discard the branch. And in this solution proceeding of the model, we notice that this is FASTMIN or cut this branch, cut this branch. And when you cut all the branch, you will finish the problem, solve the problem. So we get the optimum solution of this problem is these solutions. The objective is 14, and the optimum solution is x equal to 1, 1, and 0, 0. So with summary of the BIP solution by branch and bound oscillator, steps for each iteration. Branch among the remaining subproblems, select one that was created most recently. Branch from the node for this subproblem to create 2 new subproblems by fix the next variable at either 0 or 1. That is, we choose xi 0 or xi 1 to 2 subproblems. Step 2. Bounding. For each new subprogram, obtain each bound by applying the simplex method by its LP reduction and rounding down the value of J for the resulting optimum solution. In two cases, we can bounding. If we get the integer solution, we can bounding. If we cut the branch, we can bounding. Step 3. FASTMIN. For each new subprogram, apply the 3 FASTMIN tests summarized above and discard those subprograms that are FASTMA by any of the tests. The FASTMA criteria is: Case 1. Feasible solution of the subprogram must have J less than or equal to Jc. Jc is the current objective function. Criteria 2. The subprogram has no feasible solution. Or criteria 3. An optimal solution of the subprogram has been found. So this is the procedure of branch and bound to solving BIP problem. And we noticed in this method, the important 3 steps is branch, bounding, and FASTMIN. That's okay in these lessons. Thank you very much.